LC Oscillators, New Physics, Old Mathematics. In this chapter, you will see how the electric charge Q varies with time in a circuit made up of an inductor L, a capacitor C, and a resistor R. From another point of view, we shall discuss how energy shuttles back and forth between the magnetic field of the inductor and the electric field of this capacitor, being gradually dissipated while these oscillations continue as thermal energy in the resistor. We have discussed oscillations before in another context. In mechanics, we saw how displacement x varies with time in a mechanic oscillating system made up of a block of mass m and a spring or spring constant k, and a viscous or frictional element such as oil. The latter figure shows such a system. You also saw how energy shuttled back and forth between kinetic energy of the oscillation mass and the potential energy of the spring, being gradually dissipated while the oscillations continue as thermal energy. The parallel between these two idealized systems is exact, and the controlling differential equations are identical. Thus, there's no new mathematics to be learned. We can simply change the symbols and give our full attention to the physics of the situation. LC oscillations, quantitatively. Of the three circuit elements, resistors R, capacitance C, and inductance L. We have so far discussed the series combination RC and RL. In these two kinds of circuit, we find that the charge, current, and the potential difference grow and decay exponentially. The time scale of the growth or decay is given by a time constant τ, which is either capacitive or inductive. We now examine the remaining two element circuits combination, LC. You will see that in this case, the charge, current, and potential difference do not decay exponentially with time, but vary simultaneously with period t and angular frequency omega. The circuit is said to oscillate, and the resulting oscillations of the capacitor's elementary field and the inductor's magnetic field are said to be electromagnetic oscillations. Now we look at this picture. We start from here, where the capacitor is fully charged with positive on the top, negative on the bottom, and no current in swing. In this case, the capacitor has the maximum energy. We know the unit volume electric field has half Q squared over C energy, and magnetic field in the coil per unit is half Li squared. In this case, I equals 0. Q is the maximum, so we have electric energy stored in this capacity. Total energy is concentrated here. And then what happened? What happened is the positive charge will go this way, okay? And we see we have a current, okay? And in this case, the charge is reduced, so we see the electric energy reduced and the magnetic field energy increase until the current reached the maximum. In this case, whole energy of the system concentrate on coil, magnetic field. So I is the maximum. And in this case, no charge on both plane, so Q is 0, UE is 0. And then, because of inductance L, the continue will not stop or continue, but gradually reduce. And so the positive accumulate on the bottom plate and negative accumulate on the upper top plate of the capacitor. And we will see that electric field energy increase and magnetic field decrease until the R equal to 0. And this is the maximum whole energy stored in the capacitor. We go back like this situation. Different is that charge now is moved to bottom. And we have the same process up, go back to this one. This is circulation, okay? And we know that one, the potential difference between the coil is minus L di dt. And the potential difference across the capacitor is Q over C. They are equal. So this one minus this one equal to 0. And then we know I is dq dt. So we put I equal to dq dt, we get L move here, we get second derivative of Q with respect to time t equal to plus Q over LC equal to 0. This is the second differential equation, which we call the constant and linear. We saw it before, okay? This is the potential difference across the capacity of the circuit, okay? As a function of time t, because the Vc equal to Q over C. Q changes, so Vc changes. Is auto, and this is VR. The potential is proportional to the R, okay? So actually, this is Q, this is Q situation. This is I situation. We can measure Vc and VR, and we find the Q and R situation, okay? Example, a 1.5 microfarad capacitor is charged to 57 volt. The charging battery is that disconnected, and a 12 millihenry coil is connected in series with the capacitor, so that LC oscillator occurs. What is the maximum current in the coil? Assume that the circuit contains no resistance. Now we saw from energy conservation, okay, when this is a 57 volt, all energy is here, okay, and when all the energy moves to this one, we get maximum current. This is what we have to find, the maximum current. Okay. This is the energy stored in the magnetic field in the coil, and this is the energy stored in the capacity. This is the maximum, and this is the maximum we move. Okay, maximum. So what is maximum? This 57, this coil is 1.5 microfarad. We have L, we can find I. This is a trivius, okay, it's trivius. In an actual LC circuit, the oscillations will not continue indefinitely because there's always some resistance present that will drain energy from electric and magnetic fields and dissipate it as thermal energy. The circuit may become warmer. The oscillations, once started, will die away, as the figure suggests. You see, will die away, okay? Compare this figure with the right one, which shows decay of mechanical oscillation caused by frictional damping in a block spring system. This is our system, LC system. This is a mechanical system. They are more or less the same. Okay, the magnitude decay. Okay, it is possible to sustain the electromagnetic oscillation if we arrange to supply automatically and periodically enough energy from outside source to compensate for that dissipated as thermal energy. The electrical mechanical analogy. Half X-ray is the potential energy of spring. Is equivalent to half 1 over CQ square, the electric energy in the capacitor. half mv squared is similar to half li squared. Here we see dx dt equal to v. Okay, dx dt. dq dt equal to I, so that's why they're similar. Okay, q corresponds to x, 1 over c corresponds to k. I corresponds to v, and L corresponds to m. We know in the mechanics oscillation, the omega equal to square root k over m. So k equal to 1 over c, m corresponds to L. So in electrical oscillation, the omega is equal to 1 over LC square root. LC oscillations quantitatively. The block spring oscillation, U equal to U mass, U spring. This is the kinetic energy of the block, this is potential energy of the spring. They are constant. Okay. Suppose we no resistance, no friction. And then, so du dt equal to 0. We do this one, that's mv dv dt, half cancel, kx dx dt, it should be 0. And we found v is dx dt, okay, dx dt. So in this case, v is dx dt, so this is a second derivative of x with respect to t. And this is equal to 0, that we don't have to care that dx dt. So what we get second derivative of x respect to time t plus kx over m. This is a second differential equation, linear. We know the omega equal to k, omega squared equal to k over m. And the answer is x equal to xm cosine omega t plus phi. And xm and phi depend the initial condition. Now, we go back to LC oscillator. Same reason, okay. This is for coil, magnetic field. This is called electric field in the capacitor. They are constant, okay. So with the du dt equal to 0, here you get half and it cancel out L I di dt. This is what half just cancel out. You get q what c dq dt, okay, q dt, and I is dq dt. So di dt is second derivative of q with respect to time t, okay. dq dt, the second derivative, q over c dq dt equal to 0. And from this equation, we get second derivative q with the pattern t equal to q minus q of c, or plus 1 over LQ equal to 0. And from this equation, we know omega squared equal to 1 over LC. Okay, and the q is some q cosine sine, okay. It's sinusoidal, simple harmonic motion, okay. And this is a qm, and phi depends on the initial condition, okay. And omega squared equal to 1 over LC. And this initial condition is equal to Q0 and I0. I0 is dq dt 0. This is our answer. We see the energy of electric field is Q squared over 2C. And Q is Qm cosine omega t plus phi. Okay, right? And this magnetic field is concentrated in the inductor. It's half I squared. I is dq dt. Okay. Now we do the dq dt. We find minus omega. Okay. So we have minus omega qm sine. Okay. And then we do get this answer. This omega square q square to c. And we see omega plus L is 1 over c. This is a 1 over c. So this is a q square over C sine this one. This is sine. Okay? And then we plot them. This is energy E, electric field. This is energy B, magnetic field. Okay? We plot them. We see the blue line is UE. The green line is magnetic field. We see that at any time the sun is a constant. It's constant, okay? And they all oscillate. Sample. For the situation described in the above sample, let the coil induced be connected to the charged capacitor at time t equal to 0. The result is an LC circuit like that in the first figure. And this is what, okay? And C is given 1.5 microfarad. Air is given 0.012 Henry. And at the beginning, VC is 57 volt. Question A. What is the potential difference V air across the inductor as a function of time t? Now, from this one, we know that the inductor and capacitor connect in parallel. So their voltage across is the same. So VR equal to VC. And what is the VC? VC equal to Q over C by definition. What is the Q? We don't know. We know which is equal to Q cosine omega t plus phi. Okay. Now let's see the condition. As given, okay, T equal to 0. This is a maximum voltage, also maximum Q. So Q0 equal to big Q, the maximum Q. And we put this one here, T equal to 0. So we find phi equal to 0. And phi equal to 0, this is Q over C cosine omega t. And Q over C is VC, okay, the maximum cosine omega t. We found a VC, we found omega, we get the answer. Okay. Okay. And VC equal to Q over C is 57. Okay. Yeah. Now, the big VC is 57. Omega is 1 over square root LC. We have L, we have C, we found omega. So we put this omega and the VC inside, we get our answer. VL, function time, 57 cosine 7,100 t. Question B. What is the maximum rate, dIdt maximum, at which the current I changes in the circuit? We know this one, C, L, and VC. And we know this answer, phi equal to 0. Okay. Now, dIdt maximum is we want to find. First, we find the dIdt. dIdt is the second derivative of Q with respect to time t. And we bought this one, we get minus omega squared Q cosine omega t. Phi is 0, we have proved before. Okay, so we look at the sine cosine, the maximum is omega squared Q. What is omega? Omega is 1 over LC. Q is VCC. A C cancelled out. Okay, so we get a VC over L cosine. The maximum is VC over L. VC is 57, L is given, so we get the maximum change rate. 4,800 amperes per second.